Hello, and thanks for using TickBoom, a free service that helps high school students with their math problems. I've had a student send through this proof question which asks us to prove for n greater than or equal to 3 that the exterior angle sum of a convex n-sided polygon is 360 degrees. And the twist with this question is that the student has been asked to do this proof specifically using the technique of induction. And that's interesting because I think, I guess the most intuitive way you could try and prove this wouldn't use induction at all. There's actually quite a straightforward proof for this result. And using induction actually, I think, is a little bit harder. But what I'll do is I might just, to kick things off, work through the basic proof just to help you understand what we're dealing with. And then I'll work through how you could tackle this using induction. So we want to prove for n greater than or equal to 3 that the exterior angle sum of a convex n-sided polygon is 360 degrees. And as I mentioned, I'll first walk you through the fairly straightforward non-induction based proof. So where you'd start there is you'd probably note that the sum of the interior angles of a n-sided polygon, there's a result that you'd probably want to know, which is that sum would be 180 times n minus 2, or 180 degrees times n minus 2. And that's actually a result that, again, you could probably prove that using induction if you wanted to. But for this kind of straightforward proof, you just take this as given. So from there, what you could then say is therefore the sum of the exterior angles would be equal to, basically you'll have n exterior angles of an n-sided polygon times, and each of those exterior angles would be 180 degrees minus this 180 degrees n minus 2 on n to get each individual angle, or at least their average. And so what you'd then do is you'd say this is n times, and if we get a common denominator, we'd have 180 n minus 180 n plus 360, so that's just expanding that bracket, and that would be all divided by n. These two n's would cancel, these two would cancel, and you end up with the 360 degrees as required. Boom! So that's how you would prove this result if you weren't specifically asked to use induction, but because we here are going to be using induction, we have to dive a little deeper into what's going on here. So I'll do that now. I'll kind of work through the steps. So the first step of this induction proof would be to show that this result is true for n is equal to 3, since that's the first part of our domain. A three-sided polygon is just a triangle, so what I might do is draw up a triangle. And on this triangle, I might call the interior angles, I'll call them alpha 1, alpha 2, and alpha 3. So they'll be the interior angles. And for the exterior angles, I might use a different color, but I'll call each of those corresponding exterior angles beta 1, beta 2, and then beta 3. And we're concerned with what is the sum of those three betas. So we could we could say that, maybe I'll just do it over here, beta 1 plus beta 2 plus beta 3 would be equal to, in each case they'll be 180 minus the interior angle, so 180 minus alpha 1 plus 180 minus alpha 2 plus 180 minus alpha 3. So that's each of these betas, because the sum of two angles on a straight line will add up to 180. So that's going to be 3 times 180 minus, and I can then factor these, alpha 1 plus alpha 2 plus alpha 3. And that's going to be 3 times 180 minus, and this sum here, the interior angle sum of a triangle, we know is 180 degrees. So this alpha 1 plus alpha 2 plus alpha 3 can be simplified to 180. So 3 times 180 minus 1 times 180 is 2 times 180, and that's 360 degrees. So therefore we can say the result is true for n is equal to 3. Alright, I might turn over, because for step 2 we are going to assume the result is true. So assume true for some n equal to k. And I think what's going to be helpful here is if we draw up a diagram. So we have a k-sided polygon. Now it's kind of hard to draw a polygon when you don't know the number of sides, but I think what can be helpful is if, for example, I just call the first point of this polygon P1, and I'll call the next point P2, maybe we'll have another point P3, and then I'm just going to do a dot, 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 kind of like you do when you're writing out, say, a series with k items, and then I'm just going to draw point K here. And this is how I'll visually represent our k-sided polygon. So I'll join them up. I'll go from P1 to P2, P2 to P3. I can't really join P3 to PK because there'd be however many number of other points in between, but then I can join PK to P1. And kind of like what I did in step 1, I'll call the interior angles alpha. So we'll go alpha 1, alpha 2, alpha 3 would be some angle that kind of joins to whatever the P4 line would be, and then this alpha k. And again, you kind of just have to imagine what that angle would be, because it's ultimately affected by wherever the other preceding point is. But again, we can now draw the exterior angles. So I'll just draw beta 1, beta 2. Now for beta 3, again, you kind of got to just take this with a grain of salt, but beta 3 would connect, so the beta 3 and alpha 3 add up to 180. And same deal with beta k. We could just kind of imagine it to be here. And now what we want to say ultimately in this step 2 is we're assuming that all of these betas, so beta 1 plus beta 2 plus beta 3 all the way up to beta k, we're assuming that if the result is true, that those angles add up to our 360 degrees. So that's step 2. So now for step 3, we want to show that this is true for n is equal to k plus 1. And again, I'm going to draw up a diagram, and in drawing this diagram, it's going to be helpful to compare this k plus 1 polygon to our k polygon that I've just done for step 2. So let's we'll start again with a point P1. We'll have another point P2. We'll then come over for P3, and we'll have our PK. But now we're going to have another point, and maybe I'll just put it here, PK plus 1. So I'll again and there'll be a dot 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 in between here as there was before. So let's join up these points. We can join the pk to pk plus 1, and then pk plus 1 back to p1. What I might do is I might just do a dashed line here to kind of help remind us what we were dealing with when there were only k points, when there was a k-sided polygon. So here I might call the interior angles, instead of alpha 1, I might call A1 just to help distinguish from the alphas so that we can create relationships. So we'll have A1, A2, A3, AK would be this angle here, and then AK plus 1 would be this angle here. And again, I can draw, in this case, instead of beta, I'll just call it B. So we'll have B1, and then we'll have B2, and then we'll have B3, and then we'll have BK, and then we'll have finally BK plus 1 as our exterior angles. And something else worth noting on this diagram that I think will be helpful, I might do it in red, is it's just worth noting that this angle here is equivalent to this angle. So this is our alpha 1. That is alpha 1. And I might just call this extra bit here, I'll just call it x. And this angle here, when we were dealing with our k-sided polygon, was alpha k. And I might just call this extra bit y. And something worth noting, maybe I'll just note it over here, is that x plus y plus ak plus 1, that is going to add up to 180 degrees because they are the interior angles of a triangle that gets formed as a result of our extra point pk plus 1. And I think that's the key to this proof, as we'll see as I work through. Acknowledging this is a triangle is the key to getting to where we need to get to. Some other things worth noting, maybe I'll just again note these over to the side. Whilst A1 and AK are different, all the other interior angles haven't really changed. They don't theoretically change as a result of adding an extra point. So I can say that A2 is equal to alpha 2, and that would mean that B2 would be equal to beta 2. I could say that A3 is equal to alpha 3, and correspondingly B3 would be equal to beta 3, and so on. Like I could keep doing that for all of the other interior and exterior angles. Now if I focus on A1 and AK and see how they relate to their alphas, they're not going to be equal, they have changed. So if I start with A1, maybe I'll say A1, we can see from the diagram, is going to be equal to alpha 1 plus x. A1 is the sum of these two angles. So if I then want to convert that into, or help apply that into what is B1, the exterior angle, which is what we really care about, B1 would be equal to 180 minus A1. That's kind of the two angles of a straight line will add up to 180. So that's going to be 180 minus, and A1 we've just said is alpha 1 plus x. So that's going to be equal to 180 minus alpha 1 minus x. And 180 minus alpha 1, if we think about our original k-sided polygon, well, 180 minus alpha 1 is beta 1. So we could then write that as B1 is beta 1 minus x. That's kind of how we're effectively adjusting our exterior angle here by x. That's what we've just shown through doing this. Now I might have to turn over, but let's do a similar thing for AK. So we can see from the diagram that AK is alpha k plus y. So we'll say AK equals alpha k plus y. And then we can do the same thing. We can think about BK, which would be 180 minus AK, which would be 180 minus alpha k plus y, which is 180 minus alpha k minus y. And similarly, 180 minus alpha k is beta k. So we can write BK is beta k minus y. All right, now we can think about, well, what is the sum of these exterior angles in this k plus 1-sided polygon? So the sum would be b1 plus b2 plus b3 and so on, plus bk plus bk plus 1. We've got k plus 1 items now. Now, b1 we just showed was equal to beta 1 minus x, so I can write that in for b1, beta 1 minus x. b2, b3 and so on, they're just beta 2 and beta 3 because we noted that all the other interior and exterior angles are unchanged, so we'd say plus beta 2 plus beta 3 and so on. Now bk we just showed was beta k minus y, so I'll write that in. And then bk plus 1 is just, it is what it is. So so I can just write that as plus, well actually bk plus 1 we could write as 180 minus AK plus 1, and 180, maybe I'll just write that, so I'll just leave it as that for now, but then we're going to link up what we're dealing with. So I'll just write this as BK plus 1 for now to keep it clean, and we'll focus on how we can simplify that later. We're going to come and link that up to this point here. But for now, let's just kind of clean this up a bit. So we can say this is equal to, and I'll just bring all the betas together. So we'll get beta 1 plus beta 2 plus beta 3 plus and so on, up to beta k. And then we've got this plus bk plus 1 that we've left as is. And then we've got a minus x and a minus y. And now here we can see this first bit here gives us our link to our assumption in step 2, because that's what we've assumed to be 360 degrees. So I can just write that in now. I can just write, so that's 360 degrees plus bk plus 1 minus x minus y. Now bk plus 1 is by definition 180 minus a k plus 1. So 180 minus a k plus 1 is that there. And then we still have our minus x minus y. And I might write that as equal to 360 degrees plus 180 degrees minus, and then I'll factor out the minus. So we'll get ak plus 1 plus x plus y. And this is where we can now come back and have a look at this link, because ak plus 1 plus x plus y, that's 180 degrees. So I can write this as 360 degrees plus 180 degrees minus 180 degrees. These two cancel, and that leaves us with the 360 degrees. So therefore, it is true for n is equal to k plus 1. And that brings us to our final step. I'll just write by induction. You could write the full wording out if that's what you're expected to do. But I'll just say by induction, we can conclude that the sum of the exterior angles of a, and what's the wording we used? Of a convex n-sided polygon is 360 degrees. Of a convex n-sided polygon is 360 degrees. Alright, so that's that question done by induction, but remembering that if you weren't asked to use induction, I don't think you would. You just probably make use of this result around the interior angles, and then it's a very straightforward proof. So I think doing it by induction does force us to really think about what's happening, particularly with step 2 and step 3, and kind of drawing out these polygons and kind of seeing that what's really happening when we add an extra point to the polygon. We're kind of adjusting 2 of our angles, but everything else kind of remains unchanged, and that was the key to then being able to show what we had to show. If you found that explanation helpful, please be sure to give it a like. And if you're someone who wants to keep their finger on the pulse with the kinds of questions that other students are struggling with, please be sure to subscribe to my channel so that you can stay in the loop. Alright, tick boom!